Hi folks, Mr. Ackerman here. Thanks for watching. Today's topic is section 7.3, the movements of Earth and the Moon. We're going to be working out of the textbook On Science 9 by McGraw-Hill Ryerson. The topics that we'll cover in the video include the rotation or the spinning, and also the orbit or the revolution of both the Earth and the Moon. We're going to look at how the tilting of Earth as it rotates leads to the changing of the seasons throughout the year. We're also going to look at the different phases of the moon, meaning full moon, quarter moon, new moon, and so on. And we're going to look at solar and lunar eclipses, and we're going to finish off with a brief study of what are known as ocean tides. So let's get started by taking a look at the book. As you can see in the book, we start off with a discussion of the Earth's motion. And one of the things that the textbook does not do in this section, not specifically, so I'm going to do it, is talk about the first and most basic kind of motion, and that's the spinning. As you can see in the picture here, the Earth seems to be going around the Sun. That's what I call orbiting, or you may hear the word or see the word revolution. But it's also got another kind of motion. You can see this arrow here shows that the Earth is spinning, and they call that down here rotation. So to give you an idea of what the two might look like in real time, I've got a few videos I'd like you to take a look at. This one here called How to Spin a Basketball. Watch what this woman is doing. I'm sure you've all seen this before. She is spinning a basketball, and this is known as rotation. So the Earth is actually doing this. It does it once every 24 hours, and I think many of you know that that's how we get day and night. We're going to see that in another video in a moment. Another kind of motion that the Earth is undergoing is called its orbit, or its revolution, and you can get an idea of that if you watch a car race where the cars are kind of going around and round in a circle. Here you see a car race where the cars are going on an oval-shaped track, and this is known as orbit or revolution. So getting back to the textbook here, now this diagram makes a little bit more sense. If I go to one other video, which I have for you, and that is this one here, if I run this for a little bit, you can see the Earth is spinning and the Sun is that every time the Earth spins, different parts of it are going from darkness into bright areas. And that, of course, is where we are on the nighttime side of Earth and the daytime side of Earth. Now, while all this is happening, the Earth is also moving around the Sun, which you're going to see in a moment. So let's just wait for the video to get to that movement. I think it starts around here. You can see that the Earth is spinning around the Sun, and that, of course, is called the orbit. So now I hope you have a better understanding of what we mean by rotation or spinning and orbit or revolution. Now there's one other interesting thing about the Earth which you can't really see when you watch someone spin a basketball like in here. And what that thing is that as the Earth spins, try to imagine this woman tilting her arm onto an angle like this. If she could spin the ball on an angle, what would it look like? Well, we'll go back to the video here, and you're going to watch it, and notice that the angle of the spin is kind of tilted a little bit. And you can see that from this red line here. I'll go back a little bit to make it a little bit easier to see. See the red line there? That's called the rotation axis. And you can see it's not straight up and down like the basketball. It's tilted a little bit. And as a result, watch what happens when the Earth goes around the Sun. Sometimes, like right around now, the North Pole is pointed kind of away from the Sun. And at other times, and the south end of the Earth, not exactly the South Pole, but the southern rotation axis is pointed toward the Sun. Now as we go around, we get to this point where neither part, the north or the south, are really pointed toward or away from the Earth. They're kind of neutral. And then you get to here, where the north end is kind of tilted toward the Sun again, and the south end, it's kind of hard to see, is tilted away from the Sun. Now, if you know a little bit about the Earth and the Sun, then you know that the time needed to go all the way around this orbit is 1 year. That's how we know a year has gone by, because we've made a complete orbit or revolution around the sun. What this means is if December is around this time, that's the winter, start of winter, then June would be around this time, start of summer. And of course, sometime in March would be here, and sometime in September would be there. So these would be the times of the seasons as we know them. Now think about this for a minute. Why is it so hot in the summer? Well, a lot of people think it's because the Earth is closer to the sun in the summer. But actually, when it's summer here in Toronto, the Earth is actually a little bit farther from the sun than it is in December. And this is kind of strange, but it's true. Now, it's not a huge amount. This diagram is kind of exaggerated. However, there is a small difference. And so it can't be that the difference in distances causes the seasons. Otherwise, it would be colder in June in Toronto than it is in December. Instead, it's got something to do with the tilt of the axis. And I'll show you this in another picture. So let's have a look. This is also in your textbook, but I'm just going to show you it here because it's a little bit easier and I can do some drawing. As a result of the southern or the northern part of Earth pointing toward the sun, if you watch the rays of sunlight, they're a little bit more direct in the northern hemisphere and a little bit less direct in the southern hemisphere. I'll show you what I mean. If you take a look at this diagram, which is in your textbook, you can see that very direct light, shown by this flashlight, causes the light to be concentrated in a small circle. But when the light is hitting the Earth on an angle, like it is over here, less direct, the light gets spread over a much larger area. And as a result of being spread over a larger area, all of that light energy is not getting to heat the ground as much as if it were more direct. You're kind of spreading out the energy over a larger area. As a result, when the Earth is here in its orbit, the northern hemisphere gets direct sunlight, which makes things hot. We call it summer. But in the southern hemisphere, I don't know if you knew this, it's actually winter because the light rays are much less direct. And that situation reverses when we get over here. Now, the northern hemisphere is getting less direct sunlight, and the southern hemisphere is pointing toward the sun. It's getting more direct sunlight. So this is winter in the north, but summer in the south. So you could always have nice summer weather if you wanted. You would just have to live in the northern hemisphere in months like in and around June, and then you'd have to go to the southern hemisphere for months in and around December. Of course, in March, spring, and in September, autumn, there's really not much difference. The temperature is much more uniform across the globe. Now, continuing on in the book, we've now answered the question of why we experience seasons, and we're going to try to answer the next question, which deals with the moon's orbit. It's not just the Earth that's going around the sun, it's also the moon that is going around the Earth. And you can see that in this diagram here, where the textbook shows you the moon going around the Earth. Now, if you know a little bit about the moon and its orbit, you know that this time required to make one orbit is approximately 4 weeks, or about 1 month. I think it's roughly 27 days. And as the moon goes around the Earth, we actually get to see different parts of the moon, what we call different phases, which are shown by these diagrams here. Sometimes you get a full moon, you get to see the entire half of the moon that's facing Earth. Sometimes you only see half of that half, which we call a quarter, when we're 1/4 of the way through the orbit. Same thing happens over here. And sometimes you get to see nothing because the wrong side of the moon is lit up, call that a new moon. And sometimes you see a little sliver of the moon kind of in between the new moon and one of the quarters. That's called a crescent. And then you can be almost full. That's called a gibbous moon. So let's take a little bit closer look in the diagram here, which I've copied from the textbook. So what's going on here? Well, let's imagine that the moon is in this phase right over here. So look at the sunlight. It's coming in, and it's hitting this side of the moon only. It's not hitting this side at all. So when you, standing on Earth, look up in the sky, what do you see? You see half of the moon lit up, and you see the other half not lit up. It's kind of a circle that's half and half, and that's this image right here. You get to see a quarter of the moon. And remember, think of it as a quarter because if we're going all the way around this circle, we are now 1/4 of the way around. Don't think of it as a half moon, which some people call it because half of the circle is lit up. That's not the correct term. If the moon is over here, now it's getting hit by all the sunlight. All that sunlight is coming in and hitting, and we're getting to see it, especially at night. We're on the nighttime side of Earth here, and we look up in the sky, and what do we see? All of that lit up. That looks like a full moon. And I think if you think of it this way, you'll be able to figure out why you see all of these other phases. So those are called the phases of the moon. We've now answered the first three questions, or first three topics, and we're going to go on to the last two, solar and lunar eclipses first, and then ocean tides. So let's continue in the book as we move along. Something interesting can happen. Because of the way the Earth and the Moon are oriented or lined up in space, it's sometimes possible for the Moon to go behind the Earth, with the Earth in the middle and the Sun on the other side. Now let's take a look at this diagram a little more closely to see what can happen here. If that happens, you might get what's called a lunar eclipse. Now what does the word eclipse mean? Eclipse basically means to block something. So when we're talking about a lunar eclipse, we're talking about the moon being blocked by the Earth. The opposite of that is a solar eclipse, where now the moon, which used to be on this side, has gone around and is now here, which I see in this picture. Just going to undo those two drawings so we don't get confused. So the moon is over here now, and it blocks some sunlight and casts a shadow on the Earth. So really what we're talking about here are shadows. The Earth makes a shadow on the moon gets blocked, it's a lunar eclipse. The moon makes a shadow on the Earth, part of the Earth gets blocked, and is called a part of the sun gets blocked, and this is called a solar eclipse. We see a shadow on the Earth. Now what do these look like? Well, if you're standing on Earth at a time when there is a lunar eclipse, and you look up at the moon, you won't see the moon totally dark the way you might think. It's in the shadow, so you might think it would be totally dark, but for reasons I'm not going to explain right now, it gets a little bit darker, but it turns very red. And I'll leave it to you to find out why that is the case, but I'll give you a hint. It has something to do with the reason why sunsets look kind of red. If you want to find out more, look that up. Why is a lunar eclipse red? Since the Earth is so much bigger than the moon, the entire moon can be in the Earth's shadow, and so it can all be completely swallowed up and look dark and even red. On the other hand, if the moon is over here, the moon is much smaller than the Earth, and therefore it casts a small shadow on the Earth, and so one little part of the Earth is going to be dark. If you happen to be in that place when this lines up, then everything will turn dark, and here's what it might look like. The sun could be totally blocked out by the moon, and this is called a total solar eclipse. Sometimes the eclipse is not complete, and there are other different kinds of eclipses, but this is kind of the classic kind of eclipse. Okay? Now you might be thinking, hey, wait a minute, these two situations are what we just discussed over here. Like, isn't the moon blocking the sunlight, and shouldn't it be casting a shadow on the Earth over here? And maybe you're thinking, when the moon is here, shouldn't it be in the Earth's shadow? Shouldn't there always be a lunar eclipse and a solar eclipse? And the answer is no. This is a two-dimensional diagram. It's possible, if you were to look at this in 3 dimensions, like it really is in space, it's possible for the moon to be maybe a little bit out of alignment with the Earth and the sun in this location and that location. So you might actually not have perfect alignment and therefore not have an eclipse. In fact, the eclipses don't happen too often. The solar eclipses, I think, are more rare than the lunar eclipses. It's also harder to be in the right place on Earth to see that little shadow. It's much easier to be on one side of the Earth that's nighttime and see the darkened moon. And I'll let you think about that a little bit more. But that's kind of the way it is with eclipses. You don't get to see them too often, and the lunar ones are much more frequent than the solar ones. So we're going to wrap up with our last topic, which is called ocean tides. Now, if you've ever been near the ocean, you know that sometimes the water level gets really high and sometimes it gets really low. And it's not just the waves, there's something else going on. What's going on? Well, to see what I'm talking about, first let me show you a video that's really, really cool. Here it is. I'm just going to play it, and you can watch. This is a time-lapse video, so you're watching a sped-up version of a video which was filmed over many, many hours, probably 5 or 6 or maybe even 7 hours. The people look like they're running around because the video is sped up, but look at the ocean. It's rising a lot. Now there's people kayaking there, and now it's going back. And the people are coming out on what used to be underwater. And if you watch the shadows, watch this again. If we start back at the beginning and you watch the shadows, look what's happening. The shadows are going this way, meaning the sun is somewhere over here. But near the end of the video, if we go back and look at the shadows, you're going to see, hold on, you're going to see the shadows are now the other way, which means that the sun is somewhere over here. In other words, it started here and went all the way around. This is a full day from sunrise to sunset. So you're watching 12 hours worth of time. The water went from low to high to low. Why did it do that? Again, if you take a look in your textbook, you'll see, as I scroll down, there's 2 diagrams here, or 1 diagram, which I'm going to look at in more detail in a minute. And here's a photo kind of showing you what you just saw in the video. But let's go back to the diagram here. The idea is that the force of gravity is responsible for tides. Maybe you've heard of Sir Isaac Newton. He is credited with many things. He lived a long time ago, around 300 years ago, and he is someone who figured out the mathematical formula for gravity. What is gravity? It's a force that pulls objects toward one another. And it gets stronger if the objects are more massive, if they're heavier, and it's also stronger when they get closer to one another. So here's how ocean tides work. Basically, the moon is a massive object, and so is the Earth and its oceans. And so the moon pulls on the Earth's ocean, and some people say, well, what's really going on here is that the moon is pulling the oceans on this side toward it, and because this side is close to the moon, because the distance is small, there's a lot of pulling. Meanwhile, on this side, the ocean is farther, and therefore there's less pulling. And so you can kind of imagine someone being pulled in 2 different directions, or not 2 different directions, but being pulled by different amounts on different sides. Imagine your arms, put your arms out to your side, and imagine one person pulling one of your arms to the right really hard. And imagine someone else also kind of pushing your left arm kind of to the right, but not very hard. What's going to happen is there's going to be more pulling on this side than there is on that side. You're going to stretch out a little bit. And so some people say this is why there are 2 tides on Earth, a high tide on both sides, like this. And similarly, they say that the ocean bulges like this, turns into an oval shape, and therefore you get low tide on these sides. Now, while this is happening, keep in mind, the Earth is spinning around once every 24 hours. So maybe if this is like 12 a.m., then when you go around this way, this will be 6 a.m., and then you keep going around, and this will be 12 p.m., and then you go around some more, and this will be 6 p.m. Look what we've got. From 6 a.m. high tide to 6 p.m. high tide, Or 12 a.m. low tide to 12 p.m. low tide, what is that? That's half a day. That's 12 hours. Well, guess what? That's what we just watched in this video that I showed you about the tides, 12 hours, sunrise to sunset. Now, as it turns out, if you watch another video, which you can see the information for here, I'm sure you'll love this title, What Physics Teachers Get Wrong About Tides. Go watch this, it's kind of interesting. The explanation I gave you about tides is only partly correct here. If you want to watch an interesting video and tell me what I'm doing wrong here and be able to kind of laugh at me for a change, well, maybe you laugh at me all the time, I don't know, go watch this video, it's kind of interesting. But that's the basic idea, is that there is a heightening of the water on the near side to the moon and the far side at any given time. And as we spin around, we move through those regions, and so we get high and low tides. Anyway, that's it. I hope you learned a little bit about the Earth and the Moon and their motions, a little bit about gravity. I will see you guys in class. Thanks for watching.